What is astrophysics? It's a simple question with, honestly, a universe of an answer. In short, it's the branch of science that uses the laws of physics and chemistry to understand the universe. It seeks to explain the birth, life, and death of stars, planets, and galaxies. But really, we are not just living in the universe. The universe lives within us. Every atom in our body, from the calcium in our bones to the iron in our blood, was forged in the fiery heart of a star that exploded billions of years ago. Astrophysics isn't just about distant objects out there. It's actually the story of our own cosmic origins. It connects us to the grandest story of all, the story of everything. The importance of this field goes way beyond just satisfying our curiosity. It pushes the boundaries of human knowledge and technology. When we try to understand a distant quasar, we're forced to invent new tools and, new mathematics. These inventions often find their way into our daily lives, from medical imaging to satellite communication. The quest to understand the cosmos has always been a powerful driver of innovation. It really forces us to think bigger, to look beyond our immediate surroundings, and to appreciate the intricate and beautiful laws that govern existence itself. It's a humbling and inspiring journey, all at once. Think about it. We are a collection of stardust, living on a tiny, fragile planet, orbiting an average star in a nondescript corner of one galaxy among billions. Yet, we have the capacity to look up and comprehend the vastness from which we came. This is the power of the human mind, and astrophysics is one of its most profound expressions. It's the tool we use to read the cosmic storybook written in the language of light and gravity. Every discovery, every new telescope, every solved equation is like turning a new page, revealing more about our place in this grand cosmic play. So when you next look up at the night sky, don't just see a scattering of twinkling lights. See the history of the universe unfolding before your very eyes. See the stellar furnaces that created the elements of life. See the gravitational dance of galaxies millions of light years away. Astrophysics gives us the special spectacles to see this hidden reality. It transforms the silent, dark expanse into a vibrant, dynamic, and deeply connected cosmos. It is, honestly, the ultimate story of us, written across the fabric of space-time itself. Long before the word astrophysics was even coined, humanity was already in a deep relationship with the cosmos. Our ancient ancestors were the original sky watchers. They didn't have fancy telescopes or supercomputers, but they had patience and, really keen eyes. They meticulously tracked the movements of the sun, the moon, and the planets. They saw patterns in the chaos. These patterns became the basis for their calendars, their agriculture, and even their religions. The sky was not just a celestial canvas. It was a practical guide for survival, a clock, and a compass. Civilizations from the Indus Valley to Mesopotamia built elaborate structures to align with celestial events. These early observers, like the ancient Greeks, tried to make sense of what they saw. They imagined the Earth at the center of the universe, with everything else revolving around it in perfect circles. This was the geocentric model, championed by figures like Ptolemy. It wasn't correct, of course, but it was a brilliant first attempt to create a scientific model of the universe. It was a model based on observation and logic, even if the underlying assumption was wrong. They were laying the very first bricks of the scientific method, the foundation upon which everything else would be built. Their work was a testament to the human desire to find order in the universe. This geocentric view held sway for over 1,000 years. It was a comfortable and intuitive idea that placed humanity at the very center of creation. But science is not about comfort, it is about evidence. Slowly, cracks began to appear in this elegant model. Astronomers noticed that planets sometimes moved backwards in the sky, a phenomenon called retrograde motion. To explain this, the geocentric model became incredibly complicated, with circles upon circles in a complex celestial dance. It was getting messy, a sure sign that the fundamental idea might be flawed. The universe, it seemed, was not as simple as we had wished. Then came a revolution. Figures like Nicolaus Copernicus, a Polish astronomer, dared to suggest a different idea. What if the sun was at the center, and the Earth was just another planet orbiting it? This was the heliocentric model. It was a radical, even heretical idea for its time. It demoted humanity from the center of the universe to a peripheral role. But it had one great advantage. It was simpler, and explained the observed motions of the planets much more elegantly. This shift in perspective was not just an astronomical adjustment, it was a profound philosophical change that set the stage for the birth of modern science. The seeds planted by Copernicus began to sprout with the work of Johannes Kepler and Galileo Galilei. Kepler, using the meticulous observational data of his predecessor Tycho Brahe, discovered that planets do not move in perfect circles, but in ellipses. This was a crucial break from ancient Greek dogma. Meanwhile, Galileo turned a new invention, the telescope, towards the heavens. What he saw shattered the old world forever. He saw mountains on the moon, proving it was a world like our own. He saw moons orbiting Jupiter, proving that not everything orbited the Earth. His observations provided powerful evidence for the sun-centered model. But it was Sir Isaac Newton who truly brought it all together. He didn't just describe how the planets moved, he explained why. He formulated the law of universal gravitation. This single, elegant law stated that every object in the universe attracts every other object. The same force that makes an apple fall from a tree is the force that keeps the moon in orbit around the Earth, and the Earth in orbit around the sun. This was a breathtaking realization. For the first time, the laws of heaven and the laws of Earth were unified. The cosmos was not some mysterious divine realm, it was a predictable mechanical system governed by physical laws. Newton's laws of motion and gravity became the bedrock of what we now call classical physics. They allowed us to calculate the orbits of planets with incredible precision. We could predict eclipses, understand the tides, and even discover new planets. In 1846, astronomers noticed that the orbit of Uranus was not quite right according to Newton's calculations. They predicted that another unseen planet must be tugging on it. They pointed their telescopes to where the maths said the planet should be, and there it was. Neptune. This was a stunning triumph for theoretical physics, proving that we could understand the universe using mathematics alone. This was the birth of astrophysics. It was the moment we moved beyond simply mapping the sky, astronomy, to understanding the physical processes that govern it, astrophysics. The universe was now a giant laboratory, a place where we could test our physical laws on the grandest possible scale. Newton had given us the rulebook. The universe was a clockwork mechanism, and we were finally beginning to understand how it ticked. This mechanical view of the cosmos would dominate science for the next 2 centuries, paving the way for even more profound discoveries to come. For 200 years, Newton's universe reigned supreme. It was a predictable, orderly place. But as the 20th century dawned, new mysteries emerged that the old laws couldn't explain. One of the biggest puzzles was the orbit of Mercury. It didn't quite follow the path predicted by Newton's law of gravity. The discrepancy was tiny, but it was persistent. It was a crack in the perfect facade of the clockwork universe. It took a new kind of genius, a patent clerk named Albert Einstein, to see that we didn't need a new calculation. We needed a whole new understanding of gravity itself. In 1915, Einstein unveiled his general theory of relativity. It was a complete reimagining of space, time, and gravity. He proposed that space and time are not separate, static entities. Instead, they are woven together into a single 4-dimensional fabric called spacetime. And what is gravity? According to Einstein, gravity is not a force pulling objects together. It is the curvature or warping of spacetime caused by the presence of mass and energy. Think of it like placing a heavy bowling ball on a stretched-out bedsheet. The sheet curves, and a smaller marble rolled nearby will follow that curve, appearing to be attracted to the bowling ball. This was a mind-bending idea. The Earth doesn't orbit the Sun because of a mysterious force pulling it. It orbits the Sun because it is following the straightest possible path through the curved spacetime created by the Sun's immense mass. This new theory perfectly explained the strange orbit of Mercury. It also made some startling new predictions. One was that gravity could bend light. If a beam of light from a distant star passed near the Sun, its path should be deflected by the Sun's gravity. This was a testable prediction, a way to prove or disprove Einstein's radical theory. The opportunity came during a total solar eclipse in 1919. With the sun's glare blocked by the moon, astronomers, led by Sir Arthur Eddington, could photograph the stars near the Sun. They compared these photos with pictures of the same stars taken when the Sun was elsewhere in the sky. The result was clear. The stars' positions had shifted, exactly as Einstein's theory predicted. Light was indeed bent by gravity. Newton's universe was overthrown. The cosmos was not a rigid clockwork mechanism, but a dynamic, flexible fabric that could be warped and bent. Einstein had given us a new and much stranger universe to explore. With Einstein's new theory of gravity in hand, scientists began to apply it to the entire universe. What they found was, honestly, pretty shocking. Einstein's own equations suggested that the universe could not be static. It must either be expanding or contracting. Einstein himself found this idea so unsettling that he added a cosmological constant to his equations to force the universe to be static and eternal. He later called this his biggest blunder. But, the evidence for an expanding universe was just around the corner, waiting to be discovered by an American astronomer named Edwin Hubble. In the 1920s, using the powerful new telescope at Mount Wilson Observatory, Hubble made two monumental discoveries. First, he proved that the fuzzy patches of light called nebulae were actually entire galaxies, just like our own Milky Way, but located millions of light years away. The universe was suddenly a much, much bigger place. His second discovery was even more profound. He observed that almost all of these galaxies were moving away from us, and the farther away a galaxy was, the faster it was receding. This was the observational proof. The universe is expanding. If the universe is expanding today, it means that in the past it must have been smaller, denser, and hotter. If you run the film of the cosmos backwards, everything comes together. All the galaxies, all the stars, all the matter and energy would be crushed into an infinitesimally small, incredibly hot and dense point. This was the logical conclusion. This initial moment of creation was later, somewhat mockingly, named the Big Bang. It wasn't an explosion in space, but an explosion space itself. It was the beginning of the universe, the beginning of time, and the beginning of all the physical laws we know. The Big Bang theory made a key prediction. If the early universe was so hot, it must have been filled with intense radiation, a primordial fireball of light. As the universe expanded and cooled, this light should have stretched out, becoming microwave radiation. This leftover heat from the creation of the universe should still be detectable today, filling all of space. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, accidentally discovered this faint microwave hiss coming from every direction in the sky. It was the cosmic microwave background radiation, the afterglow of the Big Bang. It was the universe's baby picture, confirming the story of our cosmic origins. Perfect. Among the most bizarre and fascinating predictions of Einstein's theory of general relativity are objects known as black holes. These are not really holes at all, but regions of spacetime where gravity is so incredibly strong that nothing, not even light, can escape. The idea is simple enough. Imagine a star many times more massive than our sun. When it runs out of fuel, it can no longer support its own weight against the inward crush of gravity. The star collapses catastrophically. If the star is massive enough, it will collapse forever, crushing itself down into an infinitely dense point called a singularity. The boundary around this singularity, beyond which there is no escape, is called the event horizon. It is the point of no return. Crossing the event horizon is a one-way trip. From the outside, you would never see anything fall in. As an object approaches the event horizon, time for that object appears to slow down from your perspective. It would seem to freeze at the edge, fading and redshifting until it disappears. The black hole itself is by definition invisible. We can only detect its presence by observing its effects on nearby matter and stars. For a long time, black holes were purely theoretical curiosities. Many scientists, including Einstein himself, doubted they could actually exist in the real universe. But the astronomical evidence began to mount. Astronomers started finding extremely bright sources of X-rays in the sky. The theory was that these X-rays were being produced by gas being superheated as it was pulled from a companion star and spiraled into an unseen, massive object, a black hole. We also observed stars orbiting seemingly empty points in space at incredible speeds, their motion betraying the presence of a supermassive gravitational monster. The ultimate confirmation came in 2019, when the Event Horizon Telescope collaboration released the first ever direct image of a black hole's shadow. They didn't photograph the black hole itself, but the glowing, hot gas swirling around its event horizon. It was a fuzzy orange donut of light, located in the center of a galaxy called Messier 87, some 55 million light-years away. This image, a triumph of global scientific collaboration and technological ingenuity, transformed black holes from a mathematical prediction into a tangible, observable reality. These enigmatic giants are a core part of the cosmic ecosystem, shaping the evolution of galaxies. As our understanding of the cosmos grew, so did the scale of our ignorance. In the latter half of the 20th century, astronomers made a deeply unsettling discovery. When they measured the speeds at which stars orbit the centers of galaxies, they found something was terribly wrong. The stars on the outer edges were moving far too fast. According to Newton's and Einstein's laws of gravity, they should have been flung off into intergalactic space. The visible matter in the galaxy, the stars, gas, and dust, simply did not have enough gravity to hold them in their orbits. There had to be something else there, something massive and invisible. This mysterious, unseen substance was named dark matter. It's called dark because it does not emit, absorb, or reflect any light or any other form of electromagnetic radiation. It is completely invisible to our telescopes. We only know it exists because of its gravitational effects on the things we can see. It is not just a small correction either. Calculations show that dark matter outweighs all the normal, visible matter in the universe by a factor of more than 5 to 1. All the stars, galaxies, and planets we have ever observed make up less than 5% of the total stuff in the universe. The rest is a profound mystery. As if one cosmic mystery wasn't enough, another, even stranger one emerged in the late 1990s. Astronomers were trying to measure the rate at which the expansion of the universe was slowing down. Everyone expected gravity to be putting the brakes on the expansion. But two independent teams of scientists found the exact opposite. The expansion of the universe is not slowing down. It is accelerating. The galaxies are flying apart from each other at an ever-increasing speed. This was a shocking discovery that won its leaders the Nobel Prize in Physics. Something must be counteracting gravity, pushing the universe apart. This mysterious repulsive force was given the name dark energy. We have even less of an idea of what dark energy is than we do about dark matter. It seems to be a property of space itself, a kind of cosmic anti-gravity, and it is incredibly dominant. When we add up all the mass and energy in the universe, dark energy accounts for about 68% of the total. Dark matter makes up about 27%. That leaves the familiar matter, the stuff of you, me, and the stars, as a mere 5% sliver. We have explored the cosmos only to find that we are profoundly ignorant of what 95% of it is made of. The story of astrophysics is inseparable from the story of its tools. Every major leap in our understanding of the universe has been preceded by a leap in our technological ability to observe it. Galileo's simple refracting telescope opened up the solar system. For centuries, astronomers relied on bigger and better ground-based telescopes, building them on high, dry mountaintops to escape the blurring effects of Earth's atmosphere. These giant optical telescopes, like the ones at Keck Observatory in Hawaii, allowed us to peer deeper into space and see the faint light from distant galaxies, revealing the large-scale structure of the universe. But visible light is only one small part of the electromagnetic spectrum. The universe is communicating with us in many different colors of light that our eyes cannot see, from low-energy radio waves to high-energy gamma rays. Earth's atmosphere blocks most of these signals. To get a complete picture, we had to go above the atmosphere. The space age revolutionized astrophysics. We began launching satellites equipped with specialized telescopes to capture these other forms of light. Radio telescopes revealed the cold gas clouds where stars are born. Infrared telescopes, like the James Webb Space Telescope, can peer through cosmic dust to see infant stars and the earliest galaxies. X-ray observatories, like the Chandra X-ray Observatory, detect the high-energy universe superheated gas falling into black holes, exploding stars, and colliding galaxies. Gamma-ray telescopes, like the Fermi Gamma Ray Space Telescope, show us the most violent and energetic events in the cosmos. By combining data from all these different types of telescopes, we can create a much richer and more complete picture of celestial objects. It's like moving from a black and white photograph to a full-color multi-sensory movie. Each wavelength reveals a different piece of the cosmic puzzle. Beyond light, we have opened entirely new windows onto the universe. In 2015, the LIGO experiment made the first ever direct detection of gravitational waves, ripples in the fabric of spacetime itself. These waves were created by the collision of two black holes over 1 billion light-years away. This discovery launched the era of gravitational wave astronomy, allowing us to hear the universe's most catastrophic events. We are no longer just passive observers of cosmic light. We can now feel the vibrations of space-time itself. This technological prowess continues to push the boundaries of what we can know about our universe. So where do we stand today, on this day in late 2025? We are living in a golden age of cosmic discovery, yet we are surrounded by profound mysteries. The biggest questions in astrophysics today revolve around the 95% of the universe we don't understand: dark matter and dark energy. Scientists around the world are engaged in a massive hunt for the dark matter particle. They are building incredibly sensitive detectors deep underground, shielded from cosmic rays, hoping to catch the faint signal of a dark matter particle bumping into a normal atom. Others are using particle accelerators like the Large Hadron Collider to try and create these particles in the lab. The mystery of dark energy is perhaps even more challenging. Is it a constant energy of empty space, as Einstein first proposed, or is it something that changes over time? Future telescopes, like the Nancy Grace Roman Space Telescope, are being designed to map the universe with unprecedented precision. By measuring the positions and distances of billions of galaxies, they will trace the history of cosmic expansion in detail. This will help us to understand the nature of the force that is pushing our universe apart. The answer could lead to a new revolution in physics, as profound as the one started by Newton and Einstein. Another major frontier is the search for life beyond Earth. With the discovery of thousands of exoplanets, planets orbiting other stars, we have learned that planets are common in the galaxy. The James Webb Space Telescope is now able to study the atmospheres of some of these distant worlds. It can look for biosignatures, chemical clues like the presence of oxygen, methane, and water vapor that might hint at the presence of life. Finding even microbial life on another world would be one of the most significant discoveries in human history. It would fundamentally change our perspective on our own uniqueness. Our journey through the cosmos has been a humbling one. We have gone from thinking we were the center of everything to realizing we are a tiny part of a vast and largely unknown universe. But it is also an empowering story. It is a story of how a curious species, living on a small rocky planet, can use reason, mathematics, and technology to comprehend the scale and history of the cosmos. The quest continues. There are more questions than answers, more mysteries than certainties. But that is the beauty of science. Every discovery opens up new vistas to explore, ensuring that our journey through the cosmos is one that will never truly end.